Hello, welcome back to Unit 3. Today we'll be looking at Section 3.3 Technical Knowledge. And as part of this lecture, we'll look at what the important concepts are for us to become data scientists, what are the skills and knowledge within the technical domain that we need to acquire, what are the tools and languages necessary to practice data science. And we'll also see concepts such as data manipulation, languages such as SQL, Python, concepts of machine learning, and so on and so forth as part of this lecture. So to begin with, we need to have knowledge of at least one programming language. Ideally, this should be Python, as that is the lingua franca of data science, so to speak, at this point in time. And we also need to know standard query language, or SQL as it's called. We need to be able to pre-process data, manipulate data. This is important for data analytics and modeling. We need to understand what those are as well and the typical algorithms and methods that are involved therein. It's good if we are able to acquire knowledge about big data platforms and the clouds that are out there, hyperscalers, Microsoft Azure, Amazon Web Services, Google Cloud Platform, and so on and so forth. Of course, we need to know mathematics and statistical analysis. Within those tests, statistical tests and distributions, regression and classification, neural networks, SVM, support vector machines, probabilistic systems, and so on. We need to have an understanding of calculus, linear algebra, discrete mathematics, and we should also have some understanding of how to set up an experimental design for hypothesis testing, and so on and so forth. More formally, we need all of this to become a decent data scientist. Of course, it's a long list and therefore there is a learning curve involved, and we'll look at what's the bare minimum that we need to understand and acquire for us to become able enough to practice data science, and it's an ongoing process that continues throughout. So coming back to the topic at hand, we need to learn Python, and we should be aware of libraries and should be able to use libraries such as Pandas, NumPy, scikit-learn, and TensorFlow. Pandas is the library that allows us to manipulate data in data frames. NumPy has a number of mathematical operations that it provides us with. Scikit-learn is a comprehensive framework for machine learning and modeling. TensorFlow is purely focused on deep learning and deep neural architectures. In maths and stats, we need descriptive and inferential statistics, so we need to understand distributions and hypothesis testings and confidence intervals. For maths, we need to know linear algebra and calculus because these are the basic underpinnings of machine learning algorithms. For data manipulation and analysis, we need to be able to clean and pre-process data and do exploratory data analysis, or EDA. In machine learning, we should know supervised and unsupervised learning. We should be familiar with regression, classification, clustering, and dimensionality reduction. We should also know how models are evaluated, so what are the performance metrics. Some typical ones are listed here: accuracy, precision, recall, F1 score, and ROC, AUC, the receiver operator characteristic, area under the curve. We should also know database management. SQL allows us to write queries to extract and manipulate data from relational databases, or RDBMS, and NoSQL databases such as MongoDB for unstructured data. Data visualization tools and libraries such as Matplotlib, Seaborn that we saw earlier, or tools such as Tableau and Power BI, if that's relevant to your jobs. Big data familiarity with tools such as Apache Hadoop and Apache Spark or Kafka for handling large data sets. Cloud platforms, as I mentioned on the previous slide. Version control, so GitHub, GitLab's knowledge of version control systems so you can manage your code and collaborate with others. And finally, APIs and data acquisition, so you should have skills to be able to retrieve data from web services and integrate data sources as well. So let's begin with the first, and one by one we will tackle each of those topics and discuss in detail. Since this is an introductory course, we won't be going to the nth degree in each of these topics, but we will point towards future directions, other courses, and material and resources that you can use. So, what is data manipulation? This involves data cleaning. There can be missing values in data, so we should know techniques to identify and fill or remove missing data and how to handle it adequately. There are a number of driving forces depending on the task that you're trying to complete. Outlier detection, methods that you can use to manage outliers in data sets. This is very important when you're building models. And data format and data type conversions, so that you can actually ensure compatibility and correctness when you're working with the data. Transformation is another topic. You need to be able to normalize and standardize data. This essentially means that you scale it so the model performs better. Each attribute or feature in the dataset could have its own units and its own scale. And when you feed it like that into a mathematical model, a statistical model, it won't work unless you normalize and scale those features. Let's say you scale them between 0 and 1, so each value is either between 0 and 1, and you do this to all of the features, then it becomes standardized and normalized. And there are plenty of methods that you can use to do that. Encoding categorical variables, so techniques such as one-hot encoding and label encoding. Then you need to be able to know how to merge and join data sets. This is more SQL skill, but also in libraries such as pandas in Python. You need to know this as well. Aggregation and grouping, summarizing data using functions to aggregate, for instance, mean, sum, and count based on groups. Filtering and subsetting, so that you can put some condition on the data and filter the data out. Reshaping data, skills to be able to reshape from wide to long and vice versa. Some additional points under data manipulation: you might need to do data sampling. Your classes could be imbalanced. Let's say that you have a few categories in your data. Some categories have a lot of data and some classes or categories have very little data. If you're building a model, then this can have quite a significant impact on the performance. Inaccuracies and inconsistencies in data, duplication in data. You might need to drop some columns or attributes. You might have to impute and sort, transform, tabulate, and plot the data. And finally, you might even have to run some tests on the data as well as you're building the models. So what's the bare minimum that you need to know for a structured query language? You need to know the basic syntax of the select and where keywords. Select statements allow a retrieval of data from tables. Where is a conditional clause. You need to be able to create and modify tables, insert, update, and delete tables. You need to be able to join either inner, left, right, outer join multiple tables. Aggregation using group by or having filter. Subqueries, so you can nest queries within queries. Basic functions such as count, sum, average, min, max. Data types, knowledge of data types and how to work with those relational databases. So you should know how databases are normalized, what's the primary and foreign keys, and example tools such as MySQL or PostgreSQL, etc., that you should be familiar with. What's the bare minimum for Python? Understanding the syntax and structure, data types, variable loops and conditionals, functions and modules, so being able to write reusable code and using the built-in libraries such as pandas for data manipulation, NumPy for numerical operations, array manipulation, mathematical functions, Matplotlib and Seaborn for visualization, SciPy for statistical analysis, scikit-learn for machine learning, model evaluation, web scraping and APIs for retrieving data, and different databases connections for you to be able to write scripts that actually connect to databases and tables and retrieve data or store data back into those. This also includes large data sets, so using PySpark or a distributed data processing system. And then being able to write the development scripts in Jupyter Notebooks and using version control so you can collaborate and keep track of your versions. And finally, deploying your models using lightweight APIs such as Flask or Fast API, etc. Basic knowledge of using Docker for containerization is also quite desirable. So just a quick recap on machine learning. We looked at this in Unit 1 as well. Machine learning is a subset of AI. It learns from data and makes decisions, contains supervised learning, unsupervised learning, reinforcement learning, and semi-supervised learning. Supervised learning is where you have some labels and annotated labels in the data set, and the input-output pairs are known. Regression and classification are two examples here. Unsupervised is where you do clustering or dimensionality reduction because you don't have predefined labels. Reinforcement learning is where the agent learns to make decisions by interacting with its environment where it operates, and it receives rewards or feedback from the actions that it takes, and this is based on some kind of a policy. The idea is to maximize that reward. Semi-supervised and self-supervised learning is where we combine labeled and unlabeled data to build models. And because algorithms and tools are released so often, this list keeps growing. And of course, we need to be more realistic when we're starting out to have a list that is doable, and we can of course learn this on the job as we start practicing data science. So a quick walkthrough. From the left hand side, we have the various Python-based open source libraries and development frameworks, Anaconda distribution, which includes various foundation libraries such as NumPy, Pandas, Matplotlib, scikit-learn, etc. All of this can be used to develop models in Python. Scikit-learn contains almost all of these algorithms that are listed in the Venn diagram for supervised, unsupervised, and reinforcement learning. But let's see what's the bare minimum to become a data scientist. Well, we should know SQL and Python. We already know that. We should get familiar with the Anaconda distribution and NumPy and Pandas. We should use GitHub for version control. Visualization can be done using Matplotlib, Plotly, and Seaborn, and all the machine learning through scikit-learn. You might need SciPy at some point, but really, or if you're doing deep learning, you might need TensorFlow or Keras. But at this point in time, we can say that scikit-learn is our first go-to point. And in terms of algorithms, we can do regression, supervised, k-nearest neighbors, decision tree, random forest. In unsupervised, we do k-means, recommendation systems, dimensionality reduction. And for algorithms that straddle both, we can maybe choose naive Bayes from the probabilistic models, Bayesian models. Deep learning, we can maybe skip and just do neural networks for now and support vector machines. Since this is not a machine learning course, we won't go through all of these, but what we'll do is take most of these algorithms and run through Python scripts to see how they are built. Welcome back to part 2 of section 3.3, technical knowledge, and we're looking at machine learning. So we've got an example on the slide here. We see an XY scatter plot. On the x-axis we see house size in square meters from 50 to 55,000, and on the y-axis we see house price in dirhams, in United Arab Emirates dirhams, from 50,000 to 5 million. And then these are just arbitrarily chosen values to illustrate this example. We can straight away see that the scatter plot is showing some kind of a linear relationship, such that if the house size increases, then we can expect the house price to increase as well. And this is certainly what the data set is showing, albeit is a small sample. So we draw a line, and that's our model. We know the equation of line, so the slope of this line will give us the angle, and the y-intercept will also give us another parameter. Let's say there's a new house that appears in the market, denoted by this x. It's a certain distance away from our linear model. That becomes the error. Because if you see, the line will give this particular x-axis value, a y-axis value of around 3.5 million, when it really is 3.7 million, let's say. So that's a 200,000 dirham model error. With different types of data and different types of shapes of data, when you plot them between two attributes, in this case, different patterns can emerge. It's not necessary that you'll get a linear relationship always. You can get a quadratic equation, you can get a random relationship, you can get a negative slope as well. So the idea would be to fit these with different types of models to be able to get as close as possible to the real data set on which it is trained, and to keep it as generic as possible to reduce the error and not be tightly fitted or overfitted to the training set. Now we were regressing because we were using the machine learning model, the linear equation, to give us an actual value, a real value. But machine learning algorithms can classify as well. Instead of predicting a number, they can predict a label. So in this case, we see there are two classes denoted by crosses and squares. And the separation in this first example is quite simple. You can draw a simple linear line, which is the boundary, and anything that falls on this side of this boundary is a cross. Anything that falls on the right on this side is a square, is the other class. In this case, we still have a linear relationship, albeit a quadratic line, and then a totally non-linear relationship because all of the crosses are surrounded by squares and there's a need to have a kernel there. So we can draw lines, curves, decision boundaries of many shapes to separate different classes, in this case polynomials, to have even more adapted or zigzag shapes depending on the data, and then we have to be careful of overfitting as well. In terms of classification, it could be a binary classification where you have two categories or classes, for instance fail or pass, or apple or orange, default or no default, or you can have multiple classes as well, so green, red, blue, orange, so on and so forth. So let's look at a few important algorithms in depth. We'll start with logistic regression, which is predicting continuous value and then applies a logistic function to the output for classification to bind it between 0 and 1, either 0 or 1, and we can do binary classification with that. We'll do a decision tree algorithm as well, which models decisions and their consequences by splitting on some kind of criterion. This normally is a purity or measure of impurity. Random forest, which is an ensemble of decision trees to improve the accuracy. Neural network, which is a interconnected nodes layers, each node having its own logistic regression, and they signal each other. We'll look at feed-forward neural network. Support vector machines, which classifies data by finding an optimal hyperplane of support vectors, which are pivotal data points. So if you imagine the example that we saw previously here, the data points that are on this plane will become the support vectors. And finally, k-nearest neighbors, which classifies data based on proximity to labeled data. We'll look at Python scripts for all of these. There will be an additional machine learning course later on and some additional videos where we can look at the mathematical underpinnings of each of these algorithms. But to keep this introductory course succinct and concise, we'll look at the Python scripts and move on to the next topics in technical knowledge. So here, logistic regression, we see we're using scikit-learn, which is the foundation library in Python, which provides us most, if not all, of the machine learning algorithms. We say from sklearn, we're going to import, especially from sklearn.model selection, we'll import train, test, split, so we can split our training set into our data set into train and test. We'll train on the training set and we'll test it on the test set so that we don't overfit to the training set, and we can generalize or have some measure of generalizability using this test set. Then we bring in the linear model from sklearn, which has the logistic regression algorithm. And from metrics in sklearn, we import accuracy score so we can measure how the model evaluation is going. We load some arbitrary data set, in this case customer data.csv, which has two features and some target variable, because this is a classification and it's a supervised machine learning. We split our data set, which is in df, by providing both x and y, because in x we have put df's attributes feature 1 and feature 2, and in y we've given the target class, so now we're using x and y here. We give the train test split to say x is the number of features in the training set, y is the target class, and we want to split it into a train test split for x's and train test split for the y's, so that we know what labels are for features 1 and 2 in y train and y test. We give it a test size so that we say that 70% of the original data set is going to go in train and 30% will go into test. And we give it a random state 42, which is the initialization. We train the model by calling logistic regression, which we've imported already from sklearn.linear model. We pass it xtrain and ytrain. The X train contains 70% of the original data set and only feature 1 and feature 2 attributes, and ytrain contain the labels in target class for those data instances. We pass those to the fit function for model, which trains the model, and then we test it by calling model.predict by calling it on xtest. If we actually do this on xtrain, then we'll be overfitting and testing it on the same data set that we've trained on. And that's not unseen data, so it's always better to use the test set so that we have a measure of how overfitted or underfitted our model is. It's the model.predict function stores its output in y_pred. We evaluate this by passing y_test, which are the actual labels for this x_test, and the predicted labels. And accuracy score compares the actuals versus the predicted and puts an accuracy score, which we print out using the print and f statement. Model accuracy will give up to 2 decimal points, a floating point number, which will have the accuracy score. Decision tree is a flowchart-like structure used for classification and regression tasks, and how it works is that it splits the data sets into subsets based on some feature values, creates branches that lead to decision outcomes in the leaves. In Python, we do it so that we can import the tree from sklearn.tree. It's called a decision tree classifier. Again, we'll do the train test split import from model selection, accuracy score from metrics, and this time around we have the iris dataset, so we're loading iris dataset from sklearn.datasets. We place the data in X and we place the data target in Y, because the iris dataset is meant for modeling, so there's separation already. We split it using the train test split. In this case, we use the exact same arguments here as before, and we call the decision tree classifier into a model. We fit it by passing it xtrain and ytrain, which is the target class for these features or those data instances in the features. We predict it by calling model.predict on xtest and not xtrain, as we did before. Save it in y_prediction. Accuracy score function is called with ytest, which is the actual labels for ytrain data instances, which is 30% of the original data, as you can see here, test size 30%. And the accuracy score compares the actual labels of ytest against the predicted labels. And this is again printed out. So it's quite simple to call and run these algorithms, really. Of course, you should understand the details of it and how the mathematics and statistics work in the background, but that is for another course where we will do deep dives into machine learning algorithms, and you can then have a bit more complicated and comprehensive Python scripts to build models. Random forest is an ensemble method that combines multiple decision trees, and this improves accuracy and also has some control on overfitting. It aggregates the predictions of individual trees using a bagging approach, where it can essentially average out the predictions. We're doing the exact same thing as before, with the only difference being the random forest classifier, which is being imported from sklearn.ensemble. We load the iris dataset, separate into x, y, the data and target, and we do the train test split exactly as before. We call the model, and here there's a bit of a difference. We have to give it the number of estimators. So in this case, we say we want you to have the number of estimators at 100. The initialization is done with a random state equals 42 as before, and then the model is fitted using model.fit on xtrain with ytrain labels. We do the predictions again the same way. We're calling model.predict on xtest and not xtrain. We compare the ytest actual labels against the predicted labels using accuracy score. Neural networks are inspired by the human brain, and they consist of interconnected nodes. They are organized in layers, and each of these nodes is essentially doing logistic regression. The components are input layer, which receives input features from the training data set, hidden layers that are in the middle that perform computations and transformations, and the output layer, which produces the final output or prediction. If there's a binary classifier in the neural network, you'll only have one neuron in the output layer, because if it's 0, then it's one class. If it's 1, then it's another class. Similarly, if you have multi-class classifier, then you might have multiple nodes in the output layer. Over here we have the exact same configuration as well in the imports, except that you're importing MLP, multi-layer perceptron classifier, which is the feed-forward neural network from sklearn.neural network. You're loading the iris dataset, calling the train test split exactly as before, calling the MLP classifier by giving it the hidden layer size to say that it's got 10 layers, each with 10 neurons. Maximum iterations for training should be 500. Again, the random state set to 42 for initialization. Model.fit with xtrain and ytrain, predictions on x-test stored in y underscore pred, and accuracy score compares the actuals in y underscore test against the predicted actuals or predicted values for the same instances as in x-test. Neural networks have grown into deep learning, and this has really allowed computer vision, NLP to and lots of other areas to have a lot of advancement in recent years. And we saw this example in the first unit as well. Just a quick recap that you can have very complicated neural networks and different types of layers where different types of operations are happening, such as convolution and pooling. This becomes a convolutional layer. The input image is transformed, fed into this convolutional layer, reaches the fully connected layer, and then eventually the output class, which in this case is classifying whether it's a guava or a peach or a pomegranate or an orange or an apple. And in this case, as we can see, that it's correctly classified it as an apple. There are many applications such as object detection, object identification, facial recognition, classification monitoring. Intuitively, it essentially converts high-dimensional visual data to numerical representation or some kind of representation to enable processing. Similarly, natural language processing, lots of large documents with unstructured text. How do you process it? You need to do some text processing. It could be text to speech or speech to text or even machine translation as well. In order to process it, you need to tokenize, lemmatize, and do some sort of transformations, feed those documents in dense embeddings, which are forming those transformations that are ingested or pushed into the hidden layers of the neural network. And then the output essentially can be a number of things. We can classify, we can do entity extraction or sentiment analysis of a piece of text, we can do topic modeling, we can do translation, and many other things. And then generative adversarial networks, which underpin generative AI to create new content, including text and image and video and audio. And we can put in text prompts to ask it questions and give us answers or formulate different passages and paragraphs for us. And some examples are given for proprietary tools that have been released over the past couple of years. So the penultimate algorithm we'll look at is support vector machine, which essentially finds a hyperplane that best separates the classes in the feature space. And this hyperplane has the support vectors on it, those data points in the training set that form that hyperplane. Types are linear support vector machine for linearly separable data, or kernel SVM, which uses different kernel functions to handle non-linearly separable data. In Python, it's very simple to load this as well. You just call sklearn.svm and import svc from it. You load the iris data much like we've done before in the previous examples. The train test split is the same as well. In this case, we know it's linearly separable, so we're calling svc and providing the kernel keyword linear. Random state is the same. We fit the model on xtrain, providing the class target labels in ytrain. We predict it by calling model.predict, because we save the svc in, again, as in the previous examples, in the model variable. And then we compute the accuracy score on the predicted against the actuals. And finally, k nearest neighbor. So KNN classifies data based on the majority class among its k nearest neighbors. So it looks around it and sees what labels surround it, and whatever the majority class is, it gets that label assigned to it as well. The parameters are the number of neighbors to consider around the data point, distance metric, so measure similarity, for instance, Euclidean distance, Manhattan, and so on and so forth. Again, we do the exact same thing, except that we call k neighbors classifier imported from sklearn.neighbors. We load the iris data, we do the train test split, we call the model with the k neighbors classifier, providing a number of neighbors as 5. We want each data point's 5 neighbors to be considered for assigning a label to it. We trained it on xtrain by providing it the target labels. That's how it's going to check what the class around each data point is. So we predict by calling model.predict on xtest. We have the predicted targets labels in y underscore pred, which we then compare against the actuals, calling accuracy underscore. Now let's look at some metrics for model evaluation. In the previous examples, the Python scripts that we've been looking at, we have used only accuracy score. Let's look at the formula for this metric. It's the proportion of correctly predicted instances, so true negatives plus true positives, divided by the sum of all possibilities, namely true negatives plus false positives plus true positives plus false negatives. What are these terms? Let's pause here and look at the confusion matrix below to understand. Confusion matrix is this 2 by 2 matrix with true and false positives and negatives to show performance of classification model. So essentially, let's say that we have actual values at the top in columns, so actual positives and actual negatives, and then predicted values, positives and negatives, in rows. In the previous examples, you saw that we always compared y underscore test against y underscore pred. Y underscore test contained the actual labels of the target class from the dataset, and y underscore pred contained the predicted labels coming from the model. So in this case, if the model predicts positive and it actually was a positive, then that's called a true positive. In other words, it's correct. And if the model predicted positive, whereas it was a negative, then that's a false positive. That's incorrect. Let's take this with an example. Let's say that we were predicting apples against oranges, and positive is to say that it's an apple, negative is to say that it's an orange. And for one of the test data instances, the model predicted positive, that means an apple, and it actually was an apple, so that's a true positive. And it predicted an apple, whereas it actually was an orange, that's a false positive. Conversely, if the model predicted negative, that is an orange, whereas it was an apple, a positive, then that's called a false negative. This is also incorrect. And finally, if the model predicted negative, that is an orange and not an apple, and the actual data instance, the actual label of it was also negative, that is an orange, then that's a true negative, and that's a correct answer. So essentially we see on the diagonal there, true positives and true negatives, which are the correct answers. So for a perfect score, these should have 1s and these both should be 0. So coming back to accuracy, true negatives, that is all oranges predicted correctly, plus true positives, that's all apples predicted correctly, divided by all of the mistakes and the correct instances, so the true negatives and the true positives, plus the false positives, that were oranges predicted as apples, and the false negatives, that is the apples predicted wrongly as oranges. So precision and recall. Precision is the proportion of true positives among all positive predictions. That is, true positives amongst all the positives that the model predicted, including the false ones, which essentially tells us how many of the labels given by the model were actually correct. Recall is the proportion of true positives amongst all actual positives. So there's a subtle difference here. TP, 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 FP, FN. Recall is actually looking at the true positives out of all of the actual positives. So how many apples did it actually miss and label them incorrectly as oranges? Precision allows us to make the outcome from the model more precise, and recall allows us to catch all of the instances in the data that we want to. Sometimes it's important for models to actually want to maximize and optimize on both of these metrics, so we can combine them in a harmonic mean, these two rates, which becomes the F score or the F1 score. That's the harmonic mean of precision and recall given by the formula 2 multiplied by precision into recall divided by precision plus recall. This image is taken from a publication for which the citation is given. You can look at this in detail at this URL. You can also find more information on the metrics that we've reviewed here, as well as additional metrics that are used for model evaluation, and I'll give some course recommendations towards the end here as well. Now, before we wrap up machine learning chapter in this section, we should look at some ways of performance improvement. So we've built a simple model without really playing with the arguments and the parameters so much in the Python script. How do we ensure, once we look at the accuracy or precision or whatever metric that we've used or selected, how do we ensure that the model is performing optimally? And if it isn't, what can we do about it? So hyperparameter tuning is one way to change the parameters, the hyperparameters in the model, and optimize them for better performance. One way of doing that is called grid search, which is an exhaustive search over a specified parameter grid, or it's a random search, can also be used, which is a random sampling of parameters within the specified ranges. And then cross-validation, which also uses multiple folds and bags and subsets of data to evaluate the model performance. Another way to improve performance is to do feature engineering. By creating new features or modifying existing ones, the model may or may not start to improve the performance and perform better. So how can we use these methods? It's fairly easy. Let's go back to another Python example where we have our familiar import calls for the iris dataset and random forest classifier from sklearn.ensemble. A new call out here to import grid search CV is being imported from sklearn.model_selection. We load the iris dataset in X and Y, the data and the target, as we've done before. We call the model random forest classifier with an initialization random state. We give a number of estimators in a list or array of 50, 100, and 153 elements, and a maximum depth of none to 10 to 20 to 30. The number of estimators is going to tell the random forest classifier how many to use each time, with 50, 100, and 150, and then how deep should the tree and the random forest be, level 10, 20, 30, or none. We pass this to a grid search CV callout. We provide our random forest classifier model variable, and we give the parameter grid dictionary. We give a setting of 5 cross-validation folds. Grid search fits X and Y, and it gives the best parameter by calling out grid_search, which is our variable here, dot best_params_, which is going to tell us which of these parameters were the best by looking at some performance evaluation metric and setting the number of estimators and maximum depth in our random forest classifier. So the second way, other than hyperparameter tuning, was feature engineering, as we saw, and you can do this as well in Python quite easily. There are a number of techniques to do feature engineering. You can do feature scaling by just normalizing or standardizing the features. You can do feature selection by choosing the most important features based on some criteria and dropping others. Or you can create new features, deriving new features from existing data, which might improve the model. So here we have sklearn.preprocessing, where we are importing standard scalar so that we can scale the features. Iris dataset as before, train test split as before, random forest classifier as before, and accuracy_score as before. Loading the iris dataset, scaling by calling standard scalar constructor into our variable scalar, and then we fit and transform X, which is our data, into X_scaled. This is going to scale all of the features in X. Now we split it. Instead of splitting X, we're splitting X_scaled. We give it the test size again at 30%, random initialization, random state initialized at 42 as always. We train the model by calling random classifier on number of estimators 100. Save it in model, model.fit on xtrain by giving it ytrain target labels. We predict on xtest, save in y_pred, compare using accuracy score, which takes actuals in y_test and compares those to y_pred predicted outcomes. And then it puts accuracy with the scaled features in front, so you can compare this on scaled features against the one that we built earlier on the random classifier method. Another thing to check here is to see that the number of estimators is the same, so you know whether it's the scaled features giving an improvement in accuracy or the number of estimators. You can use the grid search as well as we've done before to find the best parameters for random forest classifier. And as an exercise, you can take these 3 scripts and run it on your own in a Jupyter Notebook by loading the iris dataset, running random forest classifier without any changes, do a grid search with some parameter grids, find the best parameter set, run it again, see what's the impact on accuracy, and then finally do some feature engineering, essentially feature scaling as we've done here. Scale it, see if that improves the accuracy further. We'll do further machine learning deep dives which look at the mathematical underpinnings of each algorithm and build more complex scripts with practicals in a different course. But I wanted to give you a flavor of machine learning Python scripts in this introductory course. Once you get going and start doing your exercises, I highly advise you to go to websites like Kaggle and participate in projects and competitions, build your own portfolio, and that directly goes on your resume or CV, and it gives you talking points in interviews as well. You should develop personal projects and publish these notebooks on Kaggle. You can choose topics that interest you or reflect the industry needs where you are operational. You can already use Kaggle's extensive dataset repository to practice, and you can learn from the community as well by enhancing other people's Jupyter notebooks. There are free micro courses on Python, machine learning, data visualization on Kaggle as well, which you can take advantage of. And you can engage in forums to ask questions and provide answers, which will also help you to network and engage in the community. You can even collaborate with other users on Kaggle on competitions and projects. You can use Kaggle's community to find resources on common interview questions that you would find in data science and AI interviews. And you can highlight your own projects on Kaggle during interviews, as I mentioned before. It's an ongoing process. You have to learn continuously, so stay up to date with the latest tools, technologies, and best practices in data science by reviewing Kaggle and other similar websites from time to time. Regularly experiment with new algorithms and techniques, and again, looking at data sets on Kaggle and competitions will help you do that. If you aim for high ranks in competitions, then this will also boost your visibility and credibility. It will also improve your skill set as well. And this is very good for potential employers because Kaggle has a good reputation. If you're looking for a technical role and you have a good portfolio, then this will certainly go a long way towards giving you credibility and weight. Version control goes hand in hand. You have to be able to maintain your portfolio and all the work you do for your employer as well in an organized fashion. You set up repositories. You can use GitHub to do that. For each project, you have a repository to keep your work organized. You can have a directory structure, make navigation easy. It's a good practice to commit regularly, branching so that you can develop new features or experiment without affecting the main code base. You should collaborate with pull requests and collaborate with other users for code reviews and discussions, and provide as well as receive these reviews through pull requests to improve your quality of code and learn from peers. You should document your repositories and work with README files so that it explains the purpose and set of instructions, etc., and how to use it. Even after a few months when you come back, it'll help you to read this file and refresh your memory about the project. Always indent and comment and keep your code clean, extensible, modular, etc. Track issues and bugs, enhancements with GitHub issues to keep your project organized, set milestones for projects to track progress, and you can even integrate with tools. You can set up continuous integration tools like GitHub Actions to automate testing and deployment, and use tools like NBConvert or NBDime to manage and version control Jupyter notebooks effectively as well. So finally, before we conclude this section, some additional material. It's a vast field as we've seen, and we've only seen the tip of the iceberg really. There's plenty more we need to do, and that calls for different courses. So as I said, we will have different courses on each of these topics. In the first instance, all of the recommendations I've given you, you can select some of those courses and do courses on Python if you are a beginner, and SQL as well. Do machine learning. If you've already done basic machine learning, then you should go to advanced machine learning. Do some hypothesis testing courses as well. Maybe a statistics and probability course will already cover this. Start doing some Kaggle projects, and also create your GitHub account for version control and progress in an organized manner. It will help you to develop your portfolio, and that will go a long way towards getting a job in the AI industry globally as well as locally. Once you've done this, you can do deep dives in maths, stats, discrete maths, linear algebra, calculus, numerical methods, optimization. You can go into deep learning or machine learning algorithms under the hood, under the bonnet. What's the maths behind each algorithm? This will really allow you to tweak the hyperparameters yourself and knowingly set the parameters of the algorithms. It will help you build different algorithmic pipelines where multiple methods work together in the solution. You should then move on to API deployment, learn Flask, Fast API, and so on, and maybe think about working in PySpark, big data, do a certification in one of the clouds providers or hyperscalers. Also watch this space, because we're going to be releasing very soon additional videos on this topic. We'll cover the technical areas one by one, and we'll also do deep dive courses as well. So technical courses on the web, you can definitely do Stanford Machine Learning on Coursera, which is a very comprehensive, quite a good course to do, which also goes into the mathematics as well as the programming aspects of machine learning. You can do Python courses on Coursera as well. There's a Google Crash course or an IBM Python Basics for Data Science course on EDX. Or you can try to check Udacity for Intro to Python Programming. There's a good SQL for Data Science course on Coursera. And then you can do the maths and stats to do deep dives on Khan Academy. Thank you very much, and I'll see you in the next lecture.